Today I want to look at cubic equations, in particular finding rational points on cubic curves. So first I'll look at a cubic curve having a singular point, what we call a double point. So we'll have to define what a singular point, a double point, and what a non-singular curve means. The non-singular curves will be of particular interest in our next section. Those are the elliptic curves when they're cubic, non-singular cubic curves. And we'll need to define what a tangent line to a curve means. And then the technique we're going to use for constructing rational points on the curve is the method of chords and the method of tangent lines. So these two techniques work for cubic curves. Okay, let's recall what we did in an earlier section. If we had a conic section, so some quadratic equation like this, and we had a given rational point on the curve, then we can find all rational points by intersecting a line passing through the given point. Now with cubic curves, this in general is not going to work for us to find all points on the cubic curve, and in fact it doesn't even yield new rational points for most cubic curves. But if we have a singular point, we can use this technique. So let's start with the following example. I want to find all rational points on the cubic y squared equals x cubed minus 3x plus 2, which happens to factor like x minus 1 squared times x plus 2. Okay, let's see what the graph of this would look like. So we'd have two different branches. Y could be the plus or minus square root of this quantity, so plus or minus the absolute value of x minus 1 times the square root of x plus 2. So we would certainly need x to be at least negative 2 in size. And if we want to find where the derivative is 0, well certainly you have y is 0 and x equals 1 and negative 2. But now if we want to calculate y prime, we get 2y y prime is 3x squared minus 3. So that's x squared minus 1x minus 1x plus 1. And so y prime is 3 x minus 1 x plus 1 over 2 times y, and y itself has this absolute value type of quantity like this. So you'll have that type of thing. And so y prime would be 0 when x is negative 1. We can't say it vanishes at plus 1. You're going to have a type of corner at that point. So y prime is 0 at x equals negative 1. Okay, now let's graph this curve. So this is the y-axis, the x-axis. So we have the top branch here. So x is 0 when x is negative 2, we're 0. When x is 1, we are 0. And when x is 0, we're at the square root of 2 right there. And then the derivative is equal to 0 when x is negative 1. And when x is negative 1, y is equal to 2. So we come up this high. Derivative is 0, passes through this point, comes down here, and then this is always positive. So we're graphing the upper branch right here. So what happens when we hit plus 1? Well, when x is close to 1, y is roughly equal to square root of 3 times the absolute value of x minus 1. So it looks like a type of absolute value curve here, and then it just bounces up, and then the curve looks like an x to the 3/2 power as we get large. Okay, and then we have the lower branch with the negative sign, and that's just the reflection. So square root of 2, come up here, bounce through there, and the bounce makes it look like the curves just go continuously through here. And so we have a very special point where x is 1, where it looks like there are two tangent lines to the curve. And this is what we call a double point. Got two different branches going through there. Okay, now let's try to find rational points on this cubic. So if we use the technique we did for the conics, I could start, say, with this point right here, and draw a line of slope m through it, and then find these other points of intersection. Okay, let's try that out. And there's a more accurate sketch where I have this double point right here. Okay, so we're going to draw a line through here and finding these 2 points of intersection. I'll define what I mean by a double point in a little minute here. So what is the line of slope m passing through -2, 0? So that would be y minus 0 is m times x plus 2. And so let's intersect the line and the cubic curve. So I just insert this value of y into the left-hand side, and I've got m squared x plus 2 squared is x minus 1 squared x plus 2. Cancel out one of the x plus 2's, and we get m squared x plus 2m squared equals x squared minus 2x plus 1. And just turn this into a quadratic. You got an x squared minus 2x and then minus m squared x. Put these terms over here. Plus 1 minus 2m squared equals 0. So x squared minus 2 plus m squared x plus 1 minus 2m squared equals 0. And look what happens. The solutions to this are given by the quadratic formula. So you'll have negative b plus or minus the square root of b squared minus 4ac all over 2a. And I'll let you work that out, but the point here is that we are not guaranteed to obtain rational points for a rational value of m. This may not be rational. So even though I'm starting at a very friendly point, -2, 0, the other points of intersection may very well be irrational quantities. Okay, now, suppose we started at the singular point instead. So let's draw a line through the double point 1, 0. So the line y minus 0 is m times x minus 1 this time. Intersect. So we get m squared x minus 1 squared is x minus 1 squared, x plus 2. And look what happens. In this case, we get full cancellation here, and we can solve for x. We get that x equals m squared minus 2. And then y would equal m times x minus 1, which would be m squared minus 3. Thus, given a rational slope, m, so m element of the rationals, the new point of intersection, and there's a unique new point, is a rational point. It's this point here, m squared minus 2, m squared minus 3, a rational point. So if we go back to our picture, what we're doing this time is taking the double point here, draw a line of a given slope, and there's a unique point of intersection. So we have, there's the new point of intersection. Or if I draw a slope like this, again, there's a unique point of intersection. And so we can then parameterize every point on that curve. So this gives us all rational points. Together with 1, 0. You have to throw that in. So it works just like the conic sections work when we have that double point. Okay, now before we go on to the non-singular curves, let's just define some notions here and some notation. So if we have a polynomial f of xy, a polynomial with coefficients in a given field, capital F, and let's let capital K be any field containing f. So I'll let C sub f of k denote the set of points with coordinates coming from the field capital K satisfying the equation f of xy equals 0. So it's the set of points on this curve right here with coordinates coming from the field that's in the parentheses. So for example, if I started with a polynomial with rational coefficients, so f of xy is a polynomial over q, then cf of q is the set of points on the curve with rational coordinates, or cfr is the set of points on the curve with real coordinates. Okay, so that's just some notation. What do I mean by a singular point and a double point? So a point P on the curve is called a singular point if both partial derivatives vanish at P. And a point that is not a singular point is called a non-singular point, or a simple point. Okay, now the singular points have a further classification. A singular point is called a double point if one of the second partial derivatives is non-zero. So both first partial derivatives are 0, but one of the second partials is non-zero. It'd be called a triple point if all of the first and second partial derivatives are 0, and so on. You can just keep going like that. Now a non-singular curve means a curve in which every point is simple. So there is no singularity on the curve at all. Okay, let's go back to the first example we looked at and find the singularities on it. So we had the curve y squared minus xq plus 3x minus 2, which had this type of factorization. So we first calculate the partial derivatives. Partial f partial x. is negative 3x squared plus 3, which is 3 times 1 minus x squared. Set that equal to 0, and we would have x is plus or minus 1. Partial f partial y is 2y. Set that equal to 0, and that means that y should be 0. So the singular points first of all, these have to be points on the curve where these two partial derivatives vanish. So we have 2 points indicated up here when x is plus 1 and y is 0, and when x is negative 1 and y is 0. So which of these points are actually on our curve? Y squared equals x minus 1 squared x plus 2. Well, when x is plus 1, y is 0. So that point is one of the points on the curve. When x is negative 1, we do not get y equals 0. So that's not even on the curve. So we just have a simple, just one singular point, 1, 0. And now I want to classify it as a double point or a triple point. And so I calculate the second partial derivatives. So let's start using this notation, fxx for the second partial. So that would be negative 6x. And you evaluate this at 1, 0. And already we have a second partial that doesn't vanish. I don't have to go beyond that. And we can say, therefore, 1, 0 is a double point. Okay, what does a tangent line to a curve mean? So when I'm in Euclidean space, what we did in calculus, we have an idea of what a tangent line means. It's a straight line that comes and hits the curve at one point. It's that type of notion. So the slope of the line matches the slope of the curve. Now, if you're working in an arbitrary field, we no longer have that type of geometry. Like if you're in a finite field, what does a tangent line to a curve mod P mean? So we just make a formal definition here. So if we have a simple point, and you'll see why we need to have a simple point. So simple point again means a non-singular point. On the curve, we'll define the tangent line to the curve at that point to be this straight line right here. So x minus x1 comma y minus y1 dot product right there with the vector, this is the partial f partial x evaluated at p, and partial f partial y evaluated at p. Now where did I come up with such a definition? Well, this is exactly what you would have seen in calculus. So recall, if you have a curve in the plane, some curve like this, and we're at a given point P here, and you want to find the tangent line to the curve. So the curve is given by f of xy equals 0. What do? Well, you'd form the gradient vector. So the gradient of f is partial f partial x, partial f partial y, and that has the property that it is perpendicular to the curve. So this is the gradient of f evaluated at the point P. Okay, so the tangent line here, if you take a given point xy, and then P is your fixed point x1, y1, then the set of points on the tangent line, you draw this direction vector right here, which would be x minus x1, y minus y1. You take its dot product with the gradient vector, and that should be 0. And that's exactly what this equation is saying. You've got your gradient vector dotted with this direction vector on the tangent line to be 0. So that's the motivation for calling this a tangent line. Okay, next let's look at the zeros of a cubic polynomial. So we'll need this lemma when we're getting the rational points on a curve. If I have a cubic polynomial over a given field f, and 2 of its zeros, counted with multiplicity, are in the field f, then I claim that all 3 zeros belong to that field. Proof. Okay, we could do a couple proofs. Let me outline it. So the first proof would assume that f of x factors in some extension field of capital F. So if we know that fact, then I can just use the result that says the sum of the zeros of the polynomial is minus the coefficient of the x squared term, and that coefficient belongs to capital F. So that's one way we could approach. So use the fact that the sum of the zeros is the coefficient of the x squared term. Well, let's do a direct proof, not making the assumption that this polynomial completely factors in some extension field, and just use the factor theorem. So let's let R1 and R2 be given zeros of f of x in the field f. So by the factor theorem, x minus R1 must be a factor, and x minus R2 must be a factor. So then by the factor theorem, x minus R1 times x minus R2 must be a divisor of f of x. Okay, well, what does that mean? Thus, f of x equals some polynomial g of x times x minus R1 times x minus R2, where this polynomial has coefficients in capital F. But what is the degree of g of x? This is a cubic polynomial here. These are first degree, so the degree of g of x must equal 1. So degree of g of x equals 1, and that means that g of x is really just a linear polynomial ax plus b, where a and b have coefficients in f, and therefore the third zero of f of x is just the zero of this linear polynomial, and a must not be 0, of course, because we have a genuine cubic polynomial over here. And so thus the third zero is x equals minus b over a, which is an element of the field capital F. Now I want to turn to non-singular curves. So as non-singular curve, we don't have any double point. So we're not going to be able to use that technique we saw in the first example to parameterize all the points. So there's two methods we can use for non-singular curves. We can draw chords between two given points to find a third point, or we can draw a tangent line to a curve to find a new point of intersection. So let's explore these two methods. All right, the method of chords. So here we start with 2 points on the curve, capital P and capital Q, and I draw a line joining those 2 points and intersect it with the curve. So let's just draw a little picture right here. So maybe we have a cubic curve that looks something like this. It's an example of a cubic. So this is our f of x, y equals 0. 2 given points, capital P and capital Q. So here's P, and here's Q. And we're going to assume that these 2 points have coordinates in our given field capital F, and that x1 does not equal x2. Draw the line joining these 2 points. And notice it intersects the curve at a 3rd point right here. Okay, so let's let L be the line joining P and Q. It'll have some equation y equals mx plus b, and I claim that the slope m and b must be in the given field F. And why is that? Well, the slope is just delta y over delta x. These values of y and x are in the field capital F, and therefore the slope is also in F because it's closed under differences and quotients. And then when you write down the point slope form, you'll very quickly see that the constant b is in the field F as well. Okay, so now let's intersect that line with the cubic equation. So intersect y equals mx plus b, where m and b are in the field F with this cubic, and that just means insert y equals mx plus b and set that equal to 0. Now what am I looking at on the left hand side here? So you have to remember f of xy is some cubic polynomial, maybe ax cubed, and you'll have a bx squared y and a cxy squared and a dy cubed, and then you'll have some lower order terms, and then you're putting in an mx plus b you have an mx plus b here, mx plus b squared, mx plus b cubed, and the lower order terms. And so we're going to get a cubic polynomial in x coming out, and the leading coefficient, you'll have an a, you'll have a bm, a cm squared, and a dm cubed, x cubed, plus lower powers of x. And so you can see that most values of m, this is going to be non-zero. In fact, there's at most 3 values of m that this can be 0. So if we stay away from those 3 values of m, we have a cubic polynomial. So this is, let's call it star. So star is a cubic polynomial equation for all but possibly 3 values of m. Right? Depends on how many values of m in your given field make this equal to 0. And therefore we can apply the lemma we saw before. We know what 2 of the zeros of this equation are. So x1 and x2 are given zeros. Star in F. Thus, by our lemma, the third zero is also in the given field F. x3 is in F. And then once you know that x3 is in F, the y coordinate, let's call it y3, which would be m x3 plus b, is also in F because m, x3, and b are all elements of F. Thus, we get a new point coming from our given field we started with, QED. Now, in the method of tangent lines, it's very similar, except instead of starting from two distinct points, we just start from a single point, draw a tangent line to the curve, and intersect it to find a new point. So let's let x0, y0 be a simple point on the cubic curve, so a non-singular point, and with coordinates in a given field capital F. So let's say without loss of generality that the partial derivative with respect to y is not equal to 0. Let L be the tangent line to the curve at the given point P. Then L is given by some equation, y equals mx plus b. And what's the slope of a tangent line? That's dy dx, which from calculus is minus partial f partial x over partial f partial y, and I've just written it in a different notation right here. That's going to have a value in the given field f, because all of these partial derivatives have coefficients in f, and the point P has values in our given field f. Okay, so both m and b, again, come from the given field f. And now we form the intersection. Intersect the line with the curve f of xy equals 0. So I insert mx plus b here. Okay, and I want to find the solutions to this equation. So I claim in this time that x0 is a double solution. Right, so we know that x0 satisfies this equation. That's given. So let's call it star. And we claim that it's a double zero. Now, what does it take to be a double zero? We have to show that the derivative of this function vanishes at x0. So what do we get when we take d dx of the polynomial f of x mx plus b? So again, that's just some cubic polynomial at x. So by the chain rule, we take partial f partial x times the derivative of x with respect to x, which is 1, plus partial f partial y, times the derivative of y with respect to x, and that's m. Okay, and what's this going to equal? Well, m is minus partial f of x over partial f of y. So that's minus fx over fy, and all of these are being evaluated at the point P, and we can just cancel this out, and we get fx minus fx, we get 0. Therefore, x0 is a double zero, and so once again, we can apply the lemma and say the third point of intersection, or the third zero of this cubic polynomial, has coordinates in our given field f. Third solution of star is in F. All right, let's look at an example with the tangent lines. We'll do the method of chords in the next section when we study the elliptic curves. I thought I would do one example right now. So let's take the curve x cubed plus y cubed equals 9. And there's an obvious point that satisfies this when x is 2 and y is 1. That's a solution. So I want to start at that point. Let's call it A. Draw the tangent line to the curve, and that will intersect at a new point B down here. And find those coordinates. Then I take the point B, draw the tangent line to the curve at B, and it's going to intersect the curve at a new point C. And then I draw the tangent line at C, and it intersects the curve, and you can't tell it, at some new point D, and so on. And you just keep going on constructing new points in this manner. So let's see what happens. So here's the curve. F of xy is x cubed plus y cubed minus 9. I'm starting at the point 2, 1. So we have to find the tangent line. So find the partial derivatives. So fx is 3x squared. Evaluate that at 2, 1. And we get 12. Fy is 3y squared. Evaluate that at 2, 1. And you get 3. So the slope of the tangent line is minus fx over fy, which would be minus 4. And so our point slope form, y minus y1 is slope times x minus 2. So we get y is negative 4x plus 8 plus 1 plus 9. Okay, so that's the tangent line to the curve. At the given point A. I want to intersect that with the curve. So I insert y equals negative 4x plus 9 right here for y. And you expand this out. I'm not going to belabor it here. We get this cubic polynomial, 7x cubed minus 48x squared plus 108x minus 80 equals 0. Now, being a tangent line means that 2 is a double 0. So you have x minus 2 squared is a factor of this polynomial. And so you can just do a long division, divide out the x minus 2 squared, and you end up with 7x minus 20 as the remaining factor. And so the third point, we just set 7x minus 20 equal to 0, and we get x is 27. So our new point of intersection, we have 27, comma, negative 17/7. So 2.86, comma, negative 2.43. Going back to our picture, that's right here. That's the new point we just discovered. Then we take this point, again, find the equation of the tangent line, and intersect it with the curve. And you can go on doing this, and what you'll discover is the following pattern. So let's write P1 for B, P2 for C, and for Pn, I'll write it in the form xn over zn, comma, yn over zn. So it's the nth point obtained by the tangent line method. And with a little calculation, you'll find this type of recursion, that xn plus 1 is xn times this, yn plus 1 is minus yn times that, and zn plus 1 is zn times this. So you can very quickly get the successive points using this recursion right here. So in particular, the next point of intersection we would have obtained, this point, not D, but C, that's the point C right here, is, I'm not even going to try to pronounce those fractions, minus 0.404, comma, 2.085. And what happens? How are we getting an infinite collection of points, or is it going to start cycling around on itself? Well, you can do a little work and prove the following by induction, that the xn, yn, and zn are always going to be pairwise relatively prime, that yn and zn are always going to be odd numbers, and that 2 to the n plus 1 will be the multiplicity of 2 dividing xn. And this fact here tells me that we're always going to have distinct points. Every time I go from one point to the next, I'm getting a different multiplicity of 2. And so this is telling me that we have an infinite family of rational points on that curve obtained starting from the given point A. So by just bouncing around, you generate this infinite family of points. Now, I can't claim that that's all of the points. It's a much more subtle thing to prove something of that type. All we've proven is that starting from this very easy point to find, I can find a bunch of new points.